Greetings and welcome to Lecture 4.3, Operations with Monomials. First thing I guess I need to talk about is what is a monomial. A monomial is a one-term expression that is either a constant, which is a number, or a product of a constant and one or more variables raised to integer exponents, aka this is a term. For example, -3 is a monomial, that is one term. 15x is a monomial. -23x squared y is a monomial. 49x to the fourth y squared z to the fourth is a monomial. Even 3/4 a squared b cubed is a monomial. Here's what it all has in common. Every single one of these, like a -3 or even let's say 49x to the fourth y squared z to the fourth, the only operation that's going on here is multiplication. That is one term. Where it becomes more than one term is when we include addition or subtraction. Now that we know what monomials are, we can apply some mathematical operation on them, like multiplication and division. First thing that we want to do is rewrite our products using our commutative and associative properties, which we've learned long before, and we have worked with those before. We want to simplify by multiplying our coefficients and adding any exponents of like bases. Let's see a few examples by multiplying. So I want to multiply -3x squared by 4x cubed, and our second problem is going to be 4/5 x to the fifth y squared times 10 x cubed y. So the first thing we're going to do is I'm going to go ahead and rearrange, use our commutative property to put all of our coefficients together and all of our like variables together. Well, -3 times 4 is -12. X squared times x cubed is going to be x to the 2 plus 3, leaving me with -12 x to the fifth. Let's work through the second problem. 4/5 x to the fifth y squared times 10 x cubed y. I'm going to put all of my coefficients together, which is the 4/5 and the 10. I'm going to put all my x's together, x to the fifth, x cubed. Put all my y's together, y squared, y. 4 times 10 is 40 over 5. X to the fifth times x cubed is going to be x to the 5 plus 3. Y squared times y is going to be y to the 2 plus 1. And that gets me 40 divided by 5 is 8. 5 plus 3 is 8, so it's going to be x to the 8. Y to the 2 plus 1 is going to be y cubed. So my final answer is 8 x to the 8th y cubed. Let's work with a couple of problems with division. So let's divide 15x cubed divided by 3x squared and 39x squared y cubed all over 3xy to the fifth. For our first problem, 15x cubed over 3x squared, that's going to be 15 divided by 3 and x 3 minus 2. 15 divided by 3 is 5. 3 minus 2 is 1, so it's 5 to the x1, but we don't need that 1, it's implied, so it's 5x. For the second problem, 39x squared y cubed all over 3xy to the fifth, we're going to start with putting our coefficients together again, 39 over 3, then using our properties for our exponents, it's going to be x to the 2 minus 1, y to the 3 minus 5. That leads 39 divided by 3 is 13. X to the 2 minus 1 is going to be 1, and y to the 3 minus 5 is going to be -2. Now we don't want to leave our exponent in negative form, so we're going to bring that back down to the denominator to be positive, leaving me with 13x over y squared. Now there's a second way of doing that second problem. if you think about it, if we always bring our denominator figure up to our numerator, there's a possibility that we will have a negative number, and then we'll have to bring it back down. But if you plan ahead and just bring the smaller value down to the bigger value, or the smaller value up to the bigger value, you will never have a negative exponent. For example, I'm going to bring the x up because I have x to the first and x squared is larger, so I bring my x up. My y cubed is smaller than my y to the fifth, so I bring the y cubed down. As soon as I bring it down, it becomes negative. So my problem becomes 13 over 1, which is my numbers, and then x to the 2 minus 1, all over 1, times 1 over y to the 5 minus 3. Multiply that all together. I still am left with the same solution, 13x over y squared, but all of my exponents stayed positive. If you can see it that way, to move the smaller number to the larger number, go ahead and do that. The rule still applies. As soon as you cross that line, that exponent value becomes negative. So it doesn't matter if you go up to the numerator or down to the denominator. It just becomes the opposite sign. Let's try another example. Let's divide 25a to the fifth b cubed by 50a to the a squared b to the seventh. First, we need to understand that when I'm dividing by, it's the by number that is the denominator. So it's going to be 25a to the fifth b cubed all over 50a squared b to the seventh. Go ahead and break apart, pardon me, your coefficients and your variables. 25 over 50, a to the fifth over a squared, and b cubed over b to the seventh. And you see how I'm going to start moving my exponents. I'm going to move my a squared up to my a to the fifth, but I'm going to move my b cubed down to the b to the seventh, giving me 1/2 times a to the 5 minus 6 times 1 over b to the 7 minus 3, all leading to a cubed over b to b to the fourth. Now when we multiply and divide numbers that are written in scientific notation, you're going to treat it very similarly. You're going to group your coefficients, your numbers, and then you're going to group your powers of 10. And then you won't go wrong. If you try and do the number all together, and if it's a negative exponent and you bring the whole entire number, let's say it's 2.1 times 10 to the negative 1, if you bring that whole entire number down to the denominator, that's wrong. It's just the power of 10 that comes down to the denominator. Let's first multiply an example. So I have in scientific notation 4 times 10 to the 7th and 2 times 10 to the negative 4. Well, written out, I can group my 4 and 2, and I'm going to group my powers of 10. Now you notice I've dropped this old-fashioned multiplication symbol just to save on space. If you need it there, go ahead and keep it there. So I first regroup them. Now 4 times 2 is 8, and 10 is going to be power to the 7 minus 4. So that's 8 times 10 cubed. Ultimately, I do want to write it back in scientific notation, better still 8.0 times 10 to the 3. But you do want to keep that x in there because that's part of the scientific notation. Now let's consider division. 9.6 times 10 to the 12th divided by 3 times 10 to the 4th. So I have 9.6 times 10 to the 12th all over 3 times 10 to the 4th. Again, I'm going to break it apart into, in essence, the coefficients and the variables of the 10 power. Since 10 to the 4th is smaller than 10 to the 12th, I'm going to bring it up into the numerator. So I've done the division. 3 goes into 9.6 3.2 times 10 to the 12th minus 4 10 to the minus 4 is 10 to the 8th, and now I write it in scientific notation. So that's going to be 3.2 times, using the old symbol, 10 to the 8th. So what do like terms or similar terms look like? Well, for example, 2x squared y, 12x squared y, negative 3x squared y, 1/4 x squared y, all of these have an x squared y in common. They are like terms. 1/5 xyz squared, negative 4 xyz squared. Again, they both have the variables in common, so x, y, z squared is what they have in common. They are like terms. A cubed over b, 2a cubed over b, a cubed over 15b. These are all like terms. They all have the a cubed over b in common. I understand the coefficient is not the same, but that's not what we're looking for it to be like terms. What we're looking for is that the variables with the exponents are exactly the same. These are unlike terms. Well, 2x and 2y, unlike. X is not the same thing as y. 4xy, 3x, 2y. If they are all going to be like terms, I need them either to all of them have just an x, all of them just to have a y, or all of them to have an x and a y. 1/3 x squared, negative 2x. Again, although they have the x in common, one of them is x squared and the other is x. They are not like terms. They are unlike terms. And 25 x squared y and negative 12 xy squared. Again, don't be fooled just because I have a 2 for an exponent and an xy that they are the same. The exponent has to be the same on the variable. So an x squared is not the same as an x, and a y is not the same thing as a y squared. So here's how we combine like terms. Negative 3x squared plus 15x squared. They both have the x squared in common, so I can combine them. Now I just work with the coefficient. What's negative 3 plus 15? Well, it's 12, so the answer is 12x squared. 9 x squared y minus 20 x squared y. They both have the x squared y in common, so now I can combine them. I only look at the coefficient at this point. 9 minus 20 is negative 11, so my answer is negative 11 x squared y. 5x squared plus 8x squared. Well, they have the x squared in common, so I can just add the coefficients. 5 plus 8 is 13, so my answer is 13x squared. Let's work with our distributive property and use our multiplication and simplification to work through an example. X squared times the quantity 1 minus 6 over x. So I'm going to distribute the x squared to both of the terms in the parentheses. So x squared times 1 is x squared. X squared times negative 6 is negative 6x squareds all over x. But I can reduce the second term to x squared minus 6x squared minus 1, and leaving me x squared minus 6x. Now what I'd like you to do is to work through this next problem, distribute the AB across the 1 over B minus 1 over A, and make sure that you do reduce your final solution. Go ahead and turn that problem back in to, for credit for your video problem. So that's it for this part of the video. Until next time, be seeing you.